All right, we're at chapter 19, section 19.1, heat and energy. Let's go ahead and share the uh, PowerPoint. Um, let's see, share. Here it is. Man, they have some story about you going on a camping trip in the mountains, and um, you cook some burgers, cook some 3-minute eggs, cookies, and a cake. And there's the cake. It fell. The cookies were burned on the edge, and the eggs weren't done all the way. And why is that? Well, we'll get to that later on. That's the intro. We're going to talk about heat and internal energy. Internal energy is all the energy of a system that is associated with its microscopic components, atoms and molecules, when viewed from a reference frame at rest with respect to the center of mass of the system. So this internal energy can be the vibration of uh, the molecules, rotation of the molecules, just the molecules bouncing around. It's just the internal energy. It has nothing to do with uh, adding heat to the system. It's just uh, the internal energy. Now, heat is defined as a process of transferring energy across the boundary of a system because of a temperature difference between the system and its surroundings. It's also the amount of energy Q transferred by this process. Way back in uh, chapter 8, there's an equation 8.2, delta K plus delta U plus delta E internal, which is the change in kinetic energy, change in potential energy, and change in internal energy, equals to the work done, W, Q, the heat transferred to the system, and then a bunch of T's. If you remember, there were 4 T's that transfer by mechanical wave, transfer by matter, transfer by electromagnetic transmission, and transfer by electromagnetic radiation. So that's this Q comes, we used it in that equation. Well, this is what Q, this is the transfer of energy. Now, energy transfer, a calorie is the amount of energy transfer necessary to raise a temperature of 1 gram of water from 14.5 degrees C to 15.5 degrees C. A calorie, capital C, is equivalent to 1,000 calories. Another unit of heat is the British thermal unit, BTUs. It's the energy transfer required to raise the temperature of 1 pound of water from 63 degrees F to 64 degrees F. It's a much larger unit because a pound of water is quite a bit of water, whereas a gram of water to raise it one degree Celsius, which is um, 9/5 as large as a degree Fahrenheit. Uh, it's a lot smaller quantity. So the mechanical energy, if you were to the mechanical energy equivalent of heat, if you were to hammer the nail into the wood, you are transferring energy by sound waves and the friction of the nail going into the wood. The wood would heat up, the nail would heat up. You're transferring mechanical energy. So um, uh, the change in internal energy is equal to the work plus the transfer by mechanical wave. In other words, the sound that's emanating from you hitting the hammer. Now, Mr. Joule, the James Prescott Joule, established the equivalence of the decrease in mechanical energy and the increase in internal energy. And he had this little device where the falling blocks rotate the paddles. They're equivalent blocks, so you're going to get uh, 2 mgh. By the time they fall, that's the amount. That's the change in the potential energy, and that's going to be the energy transferred to the system. The falling blocks rotate the paddles, causing the temperature of the water to increase. And he discovered that that it was 4.186 joules of energy needed to raise the temperature by 1 degrees. The 1 gram of water by 1 degree. So now the historical name for the quantity is the mechanical equivalent of heat, but a better name would be the conversion factor between calories and joules. All right, and I think that's it. Next section we'll do the specific heat and calorimetry.